Okay guys, today what we're going to be dealing with are the polynomial functions of a higher degree, and more specifically the characteristics of their graphs. Polynomials all have some characteristics that are in common that will go along with what you've learned about parabolas previously and linears and everything like that, but they also got some characteristics that are unique to them that we want to make sure we cover because they're kind of the basis for what we'll do for a lot of other things. So the first thing I want to do is talk about what do their actual graphs look like. Their graphs look like this. First of all, they're going to be continuous. So you're going to see a continuous graph. You're not going to see a bunch of dots. If you are looking at that, we want it to be continuous, which means there's no breaks or anything like that. So if I was looking at a graph, it can be really weird looking and still be that. But you look at all these things right here, that's an example of a polynomial function right there. Smooth curve, no breaks or gaps or anything like that. So this one would be good. Here's an example of something that's not polynomial, not just a polynomial function. And for instance, we've looked at piecewise functions. Let's look at another one of those. An example would be something along these lines. Even though this is a function, the fact that there's a gap in it, or you have to pick your pencil up off of your paper to finish this graph from left to right, that's going to tell you that this is not going to be a polynomial. So not a polynomial, make sure that we're aware of that. That's going to be something that will pop up in the play, and they'll ask you about those. Okay, the other thing, you're going to have some smooth curves. So let me scroll down a little bit in this direction, if it will let me. And here we go, some. Let's see if we can go down. Okay, we're looking for smooth curves. So an example of something that's a smooth curve means that it's not going to have any jagged edges or anything like that. And a smooth curve, it could have all kinds of things like that. But if you notice, like, it's rounded everywhere that I go. It's rounded. So that's what's going to make that a smooth curve. This one's not a polynomial function, so you can think of something like an absolute value would not be a polynomial because it comes to a point. So an example of not a polynomial, even though an absolute value would have done fine here, the fact that that has some specific points that it comes to and changes direction right there, that means it's not a smooth curve. So we'll just write that in there. It's not smooth. We want it to be smooth in order to be able to do that. So those are some of the basic things with the graphs on those. Now you're going to be talking about some other things with the with power functions. I'm going to let you look at that in your book because power functions, just like x squared or x cubed or x to the fourth or x to the fifth, those are examples of power functions where you're just doing one exponent to a variable and that's it. And they all have some very common characteristics. But what we're going to look at is something called the leading coefficient test now. That leading coefficient test is going to be probably the most important thing that we're going to be looking at when we look at these characteristics, because they tell you how this thing behaves as x gets really large or really small, really positive or really negative. That's the leading coefficient test. So here's what we're going to do. First of all, we're going to be able to look at this and say if the leading, let's say if the degree is even, meaning the highest exponent you see is x squared or x to the fourth or x to the sixth, then it's going to do one thing. If the degree is odd, it's going to do something else, meaning the highest exponent, that's always what determines degree, it's going to do something else. Okay? So those are the two things. I'm going to kind of organize this, and I would suggest you do something similar to this on your paper when you're doing it to make sure that you have that set up. If the degree is even, if the leading coefficient, that's what I'm going to call LC, is the leading coefficient. Leading coefficient is positive. The only thing I really want to look at in this is what happens when you get really far to the left side of the graph or really far to the right side of the graph. You can think of this one like a parabola because here's what it's going to basically look like. If the leading coefficient is positive, it's going to go up towards infinity. It can do whatever it wants on the inside there as long as it's smooth curves. And it's going to go up towards positive infinity in both directions. That's for an even degree, but a positive leading coefficient. So it's going to open upward like that. You might understand from what we've done with transformations already that if the leading coefficient in this situation were negative, it's going to open downward instead. So that's what we're going to write next. If the leading coefficient is negative, then it's going to look something like this. It can have as many bumps in the middle as it's allowed to have and everything, but it's going to open downward, so it's going to go down to the left and down to the right, and that would be the end behavior. When the degree is odd, you can think of something like x cubed. It's going to be a slash that goes like this. So the way that's going to work is still you have to look now at the leading coefficient. So if the leading coefficient is positive again, let's look at an example of what this is going to look like. It can go up or down or left or right or whatever it wants to do, but in the inside here it can have as many bumps as you want, as long as it starts out low and goes up high to the right. Low to the left, high to the right. That's going to be an odd degree, but a leading coefficient that is greater than 0. And then finally, if you're looking at this last thing here, we're going to say the leading coefficient could be negative if it's an odd degree as well. And in that case, because I'm going to hit my face over here if I'd write where I usually would, it's going to start up high. It can bump around as much as it wants to in here, but then it ends low. And those are the 4 types of graphs that you could have. So those will all come into play a little bit. So the only thing you have to look at is the highest exponent, and then what is the number directly in front of that. That's what we call the leading coefficient. So let's look at an example of what these would be. We haven't written out what the actual end behavior is going to be. And the way you always do that, let's say that our graph just looked like, let's go with the last one there. If your graph looked like that, you could say when x is getting really negative, because x is decreasing as you go to the left, you can follow the little yellow cursor. As you go to the left, this is going up towards positive infinity. So x is going towards negative infinity, but y is going towards positive infinity. The way we state this end behavior is this. As x approaches, that's what the little arrow is, negative infinity, that means we're going to the left. F of x, the height of this is going up, so it approaches infinity. And there's going to be no limit on how high or how left that can go. So that's how we would state that one. And then we would say as x approaches positive infinity, meaning going to the right, you can see if you follow that yellow dot, it's going to be going down. So the value of the function f of x is decreasing there. It's going down towards negative infinity. Let's look at one more example to make sure we have that, and then I'll wrap up this video because we're getting up there in time already. Let's say it looks like this. That was my graph. That one's going up in both directions, so what we're going to say in that one, you're going to notice that this part is going to be the same, and I'm going to highlight it in a second. As x goes really far to the left, f of x is going to be increasing, going up. And then as x goes really far to the right, we're going to see that f of x is also increasing towards positive infinity. So when you are describing the end behavior, notice what's going to happen in each one of these things, and I'm highlighting a little bit here, and I'm highlighting a little bit over here. So the only thing you really have to concern yourself with on these is when I go to the left, is it going up or down? You can see that the positive infinity, when you go to the left on both of them, like here, on that one, it's going up. So this was a positive infinity. This is going down, so it's a negative infinity. Here, it's going up in both directions, so that's why we have 2 positive infinities. So that's how we will determine end behavior, by looking at just the equation, and then we're going to be able to describe it using the method there. So when it says describe the end behavior, you're going to have one of these things that says as x approaches, y approaches, blah, blah, blah. That's how that will end up. So that will conclude this video. We'll try some of these in class tomorrow, and you should be ready to do that at that point. Thanks.